So anyways, good afternoon, everybody. I hope everyone's having a wonderful day. So just before I get started, I just want to remind you that assignment 4 is out there in the ether. Just a reminder, remember it's due mid next week. So just keep in mind that. You can start working on it, and depending on how far along we get today, you should be able to work on more of the problems. In fact, one of the core problems on the assignment involves weighted graphs. So as soon as you know what a weighted graph is, you can pretty much just start tackling it. So anyways, let's get started. So on the topic of weighted graphs, I want to talk a little bit about weighted graphs. So we talked about graphs just generally where we have edges and they have endpoints, right? The vertices. But sometimes I would like to represent more with my graph. So one natural way to extend this is by using a weighted graph. So weighted graphs much more broadly can be generalized even further than my definition here. So for example, I can assign weights or costs to the vertices, for example, or I can even have the edges represent not even just integers, they might be rational numbers, for example. They may even be even more than that. But here's the idea in a weighted graph. So all I'm going to do is assign weights and costs to the edges in the graph. So for our graph, I'm just going to assume that there's a number associated with each edge, which I'm going to call its weight or cost, depending on its context. I'll usually use the name weight, but cost also works. And for those that like fancy the mayonnaise, they like smearing on that mayonnaise on their good sandwiches. The way I could define the weight function is that for each one of the edges, I output an integer. So that's what this mapping here represents. So, and we call W of E the weight or cost of the edge. So this is very often what you'll see me writing down if I talk about a weight, is I'll say W of E. So anyways, I wanted to give you an example of what one of these might look like. So this is just a graph. I'm going to use this graph several times during this lecture. So just be wary that I will draw that graph over there very often today. So these weights can represent all sorts of different things. You got to look at it but both as just a mathematical formulation, the mayonnaise, or mustard. You can think of it like that, or you can think of it more as a more versatile way I can model using the graphs. So the weights, for example, allow me, for example, to encode distances. So you can think of the edges now as lengths. So just like in the example application I gave you where I had a flight route map, and I could have, for example, distances, or that could have represented the cost for the fuel to go from one location to another, or airport to another airport. These might represent distances. It might be some length. That's very common, especially when routing-based problems. Another one is you can think of these edge weights almost like loads that you have to carry from one place to another, where the goal is to make it so that I'm pushing some sort of load from one vertex to another, and that load that I can carry can be no more than, say, for example, that edge. Or another way you can imagine is like if I have one of these edges, I could also imagine it like the load has to be distributed to one of its endpoints by directing it. These are what we call orientation problems, for example. Another type of problem that you might run into is that you imagine say, for example, you think of this graph like a network of sites or locations, or you can think of them like computers, like a computer network. The edges might represent costs to build connections between the sites or locations. So you can think of the sites as vertices, and the idea is that if I include an edge, it incurs a cost of whatever that weight is, and if I take it out, I reduces the cost because I think of this edge like I'm building this edge. You're going to see in the problem we're going to talk about, this third interpretation is going to be very natural for us how we're going to model the problem. So if I include the edge in, think of it like I'm building the network. And so I want to plan out how I design the network. So these happen in so-called network design problems, and their applications are all over the place. Some of the earliest motivations for solving problems like these were under telecommunications. So people wanted to lay out like phone lines, for example, or say electrical power lines, for example. These are very natural problems to formulate as graphs, at least if you think of the weights like this. So one very natural question you might say is, Dan, how do I represent a weighted graph given the ways that we've talked about representing graphs? Well, one very natural and simple way is if ever you have a generalized representation, like our generalized version of an adjacency matrix, or even if we're talking about an adjacency list or its generalized form, if we have some edge object or edge data, you can just store the edge weight with that as just another attribute. So it can be as simple as that. But one thing I do want to mention, more classically speaking, is if you have an adjacency matrix, a classic way of representing a weighted graph is, and this says if, it sort of melted there. It went in the microwave a little too long. If edge E is in the graph, then I'm going to set its value in the table or our adjacency matrix as the weight of the edge. And if this edge is not present, and so if there is no edge at, say, using the endpoints U and V, I just is simply going to assign that position to be infinity, where this is some large value that doesn't represent any one of the positions in the table or matrix, however you'd like to view it. So you're just going to see it, instead of just a bunch of ones and zeros, you look at it as either the edge weight, and if that edge is not present, you just write infinity. So for example, you can think of like the diagonal, and say, for example, if we're considering a simple graph doesn't have any loops in it, right? So you know right away the diagonal, instead of it just all being zeros, you'd have infinities down the diagonal. But the point is that you could represent these weights on a graph, and they can associate one with each edge, so they don't incur any additional cost for storing these things than I gave before. They're just some other additional attribute. There's one for each edge. And the other thing is I can access each one of these edge weights if I want in constant time, assuming I have access to the edge object. So that's the two kind of big caveats. It's important when we talk about exploring the graph or manipulating or doing anything with the graph, is knowing, okay, can I have access to that or not? You can think of it very much like an OO kind of way, or you can think about it in terms of proximity, how close I am, or am I at that vertex? So is that okay with everybody? Does everybody understand the idea? Is that, oh yeah, all we're doing is adding numbers onto the edges so that I have a number associated with each one. That's all it is. So if we're okay with that, give me 2 thumbs up. Okay, so now next what I would like to do is I want to show you how I might use a weighted graph. So I'm going to talk about our first kind of 2 big problems I want to talk about on graphs that involve weighted graphs. They're 2 classics. They're from combinatorial optimization. So it always gives me an excuse to start talking about optimization problems, because these are problems you're going to encounter very often in your future studies. Because optimization problems, these are a specific kind of problem, and it actually just generalizes over the things we've talked about at the beginning of this course. It's just that there's a little bit of terminology. I just want to use this as a kind of a gateway to get you towards, so that we could talk about it. So we're going to talk about minimum spanning trees and algorithms for computing them in this lecture. So what I want to do is remind you what a spanning tree is. So remember, a spanning tree is simply a tree. So if I give you a graph G, a spanning tree T of G is a tree that contains all the vertices in G. Right? Remember, we talked about that the other day. So next, I got to talk about what it means for the cost of a spanning tree. So what is the cost of a spanning tree? It's quite natural if you think about it. In terms of the last interpretation of the graph, you can think of it like every time I include an edge, it incurs or adds cost to the tree. So the idea is very natural. If I include an edge in the spanning tree, I incur that cost. So here's the idea. So if I give you a weighted graph, if I compute a spanning tree, it's just going to be simply the sum of the edge weights of the edges in T. So just to give you an example, let's do an example here. Let me just get another colored marker here. Let's use blue. Let's go blue with this. Okay, so let's just do this. So for example, let's just do one here with us. So this is just the same graph I had at the beginning of the lecture. So all I'm going to do is I'm just gonna, I don't know, let's just pick some spanning tree. I don't know, I'm just going wherever we'd like to go with this. So I don't know, suppose we have, I think I have all the vertices here, and this is in fact a tree, right? There are no cycles. So this is a spanning tree. Can somebody tell me what the total cost of this spanning tree is? So remember, I'm just going to sum up all of the edge weights. So all the edges that are going to go into the tree. So just as a reminder, so what I would call, for example, while you're thinking about that, I would call a spanning tree for our problem here is we would think about it as a feasible solution. So notice that in what I'm going to be talking about here is we're going to be talking about trying to get the cheapest spanning tree, and a feasible solution would just simply be a spanning tree. So I want to have some way of measuring how good the spanning tree is, and that's going to be the cost of the tree. So let's see, we got 32 so far. So let's see, we got 6 plus 8. So that's 14. Then we got plus 5. That's 19, right? And then I have 19 plus... Oh man, did I include that 5 when I started adding this? Let's see, 6 plus 8, that's 14. Plus 5, 19. Plus 6, that's 25. And then, yeah, that's 32. Very good, very good. So for example, the cost of this tree, so the one in blue, its cost is, I'll just write it as blue and I'll say 32 because we sum up 6 plus 8 plus 5 plus 6 plus 7. See, I just about forgot how to do arithmetic today. Isn't that wonderful? I'm just joking around, but anyways, the question is, can I find a cheaper spanning tree? That's going to be really the question we're going to address here. And this is what we're going to refer to as a minimum spanning tree. So the goal here is we're going to try to find one of these minimum spanning trees. So given a weighted connected graph, G, the goal is I want to get a spanning tree T such that its total cost, simply the sum of all of its edge weights in that tree, is as small as possible. So you can think of it like I give you the connected graph that has weights on it, and I want to compute a spanning tree. Now, the constraints of this problem is I need to compute a spanning tree. So any such case here, if I output a spanning tree, this follows all the constraints of the problem. We call this a feasible solution. Now, in our case, we want to find the best possible answer. Now, we have a special name for that. You may have heard of this term. It's called the optimal solution. So what I would like to do is compute the optimal solution, which that is a spanning tree whose total cost is as small as possible. So this problem, we would call this a minimization problem. And the goal is, of course, I want the spanning trees where this is as small as possible, right? So the question is, what is that? So let me draw out what the minimum spanning tree would be. So I'm going to use red edges to indicate this. So in this case, the minimum spanning tree would be the ones I'm indicating with red here. I don't want to cross the red and the blue. So there we go. So there's a spanning tree. Can somebody tell me what the total cost of that spanning tree is? The one in red. Let's see. Is it, let's see here. 4 plus 3 is 7. 10. Then 5 plus 6 is 11. So this is 21. It's 21. Yeah, that's okay. That's okay. So, you know, this is much cheaper. This is an example of the optimum. So we would call the value of the optimal solution, we would call that the optimum. So the goal is to compute an optimal solution. So I'll call this an optimal solution. And many optimization problems are cast like this. I give you some constraints. So in this case, I want a spanning tree. And I want the one that's cheap as possible. The ones that are cheapest, we call optimal solutions. And I must stress that there may exist many optimal solutions, or there may even just be one. So sometimes you're going to find that there's different ways of obtaining optimal solutions, but they may not actually just be only one optimal solution. There may exist several of them. So depending on different constraints the problem has, the optimal solution may be a thing that exists only once, or it could be several different ways of getting, for example, a spanning tree that all have the same value, in this case 21. In this case, I believe this is the only one that's in this tree, but somebody could check that if they're curious. But I will mention that there are some unique characteristics for a spanning tree, in particular a minimum spanning tree, to be unique. So one thing I can mention to you is, based on the fact that these are I'm adding the edge weights. If you make all of the edge weights distinct in the graph, so if you have a graph that all the edge weights are distinct, for example, there will only exist one minimum spanning tree. That's one example of where the distinction can happen. But if I have it where the edge weights may be duplicates, so meaning say if I have multiple 3s here, it may not necessarily be the case. So this is just something I wanted to mention. So what we're going to be trying to solve is the minimum spanning tree problem. So I abbreviate minimum spanning tree using MST. So it's not some kinds of savings tax or something like that. It says minimum spanning tree. So all I need to do is, given a connected weighted graph G is equal to VE, compute a minimum spanning tree. That's what the minimum spanning tree problem is. So is the problem clear to everybody? So all we need to do is I give you one of these weighted connected graphs, and I would like to find a minimum spanning tree. So my job is to compute that. So are there any questions? Because the rest of the lecture is going to be about this problem. So if you don't understand this problem, it's going to be a big problem for the rest of the lecture. Pun intended. So if we're okay, is there any other questions before we proceed? So if we're doing okay, give me 2 thumbs up. 2 thumbs up. Wonderful, wonderful. Okay, let's head over here. And I want to talk a little bit about algorithm design with you. And this is something that you've seen throughout your studies, and I feel like I just want to really emphasize it. Is that when we design or develop or discover algorithms, depending on the novelty of what we're doing, often at the heart of this process is studying the problem that we're looking at. So oftentimes, one of the great kind of underlying things in your studies that you don't really hear enough about, or maybe you do hear about it, but maybe not enough, is that, and as we've seen in this course, very often what we do is we study what we're trying to do carefully, in particular the problem we're trying to solve. And what we do is we try to prove properties that that problem has. So for example, there may be an underlying structure that the problem has, and we try to exploit that by discovering it, by proving, for example, a theorem, the mayonnaise or mustard, the stuff that makes a really awesome sandwich sometimes. So note that is indeed something that plays a very core role in algorithm design. The algorithms often just don't poof into existence. That is, sometimes it's a matter of luck that you've come up with it through a matter of intuition. But at the level that we work at as computer science folk, we would like to try to figure out what is going on with the problem so I can tell you with certainty, with absolute certainty in our case, that the algorithm will always operate the way I'm claiming it will do. So that means I need to learn more about the problem. So one thing I want to point out to you is that by that nature, I'm going to try to figure out what's going on with this minimum spanning tree problem. So we're going to try to reveal some underlying structure that the problem has, and we're going to try to develop an algorithm around that property. And in fact, I'm going to give you a couple different ideas of how we can do that. So one thing I do want to acknowledge, as I mentioned, the minimum spanning tree problem is a problem that's motivated at its heart, at least early life, in telecommunications. For example, in the development of electrical networks or telecommunication networks. So for example, think of phone lines. That's where very often these kind of things come up. For example, the efficiency of electricity being transmitted from one site to another site. You could think of it as a network design problem where you include the edges in the tree, and I would like to have the ones that are the cheapest ones to build for the network, or you can think of it as the total cost of transmitting the electricity through the system, or even just building or transmitting things through the system. But in this case, it's about building or including edges. There are several other ways I could talk about all sorts of things with the edge weights, and those problems may get more complicated depending on what you're doing. But the point is that this is heavily motivated by earlier work in telecommunications where people want to actually build, for example, phone lines, towers, and things like that. And I would like some way of building that the cheapest way possible. And it's a very natural way of thinking about the minimum spanning tree problem. So I want to talk a little bit about this, what I just mentioned a moment ago. This whole idea that we have underlying things going on with the problems that we want to reveal. one such case is going to be something we're going to refer to as the cut property. And this plays a very important role in the algorithms that I'm going to show you today. So it's going to be very wordy at first, and then I'll explain what it means. Now, based on the time we have, I probably won't have time to go through the formal writing of the proof in its entirety, but I want to give you a sketch of what the proof is like. I have the whole proof in the notes. I would not, by the way, ask you to reverb or give me back this proof on an exam or something. I just want you to read it. It's very interesting proof. But it gives you at its heart an underlying structure that we could exploit by developing an algorithm that takes that property and takes it and just says, hey, look, this thing has this property. Let's exploit that. And we could use that to solve the problem. So I'm mostly going to write down this, and then I'm going to parse it for you, and I'll give you some idea of why it's true. So I'm going to give you just a little bit of a sketch of the idea. But the proof is in the notes, just to be very clear. So consider any weighted connected graph. G is equal to VE, where I'm going to give you two sets of vertices, V1 and V2 are two non-empty sets of the vertices of V with no common vertices. So just to parse this out first. So for those that have taken or gone through, say, 310, you might have a special name for what I've described on the board. But I want to write this out. So I'm going to have these two sets of vertices called V1 and V2. They're going to be both non-empty sets of vertices. But the thing is, these two sets, V1 and V2, they're not going to have any vertices in common. So for those that have taken a course like 310, you might know what this is actually called. We have a name for that from a set theoretic standpoint. So for example, if it is the case that V1 and V2 contain all the vertices, we have a name for this. It starts with a P. For anybody, does anybody know what I'm referring to by any odd chance? I'm not going to ask you to know about this. I'm just curious. So say, for example, if V1 and V2 contained all of the vertices of V, but they did not have any elements in common. It's a partition, exactly. So V1 and V2 partition V. So that's one way you could think about it if you're familiar with this from set theory. But it's absolutely not required for this. In fact, this property is very flexible. So I could even omit vertices in this property. So, anyways, let E is equal to UV. So this is going to be an undirected edge. Be some edge in G with least weight. Where U is in V1 and V is in V2. So now this is where the killer part of this comes in. There is a minimum spanning tree that contains E. So there's going to be these two sets of vertices, V1 and V2. And I imagine I consider some edge E. And I want to suppose that it is an edge with least weight. So it has the smallest edge weight, where one of the endpoints is a vertex in V1 and the other one is a vertex that's in V2. And remember, they have no vertices in common with each other. What this cut property is telling you is that there exists a minimum spanning tree that has this edge E in it. So let me draw you a fun picture. I assure you it will be fun. So here we go. So here's a picture to help parse out what this statement is really telling us. So normally if I had a little bit more time, I would actually sit down and actually prove this with you step by step. Instead, I'm going to give you a sketch of how this proof will play out. So suppose that I have two sets of vertices, V1 and V2. And now there may be all sorts of stuff happening between V1 and V2. For example, there could be all sorts of stuff going on in here. I don't know. Who knows? Maybe they could be doing the cucaracha or something inside of here. I have no idea. It's just some structure of the graph is in here. And there might be some edges that go from V1 to V2 from one of these guys over here. And then say V1. These folks could be doing the Macarena over here. I have no idea. There's all sorts of stuff going on here in this one other graph. But the point is that I'm telling you that if I consider one endpoint of some edge that has the least weight, that has one of its endpoints in V1 and the other one in V2, my claim is that this edge E is in a minimum spanning tree. And you might ask, Dan, how do you know that? So how do you know that? Now, the way you would prove this, so I'll tell you that the proof, so I'll just mention that the proof is in the notes. I encourage you to read it because the correctness of this algorithm is highly dependent on the algorithms I'll show you all depend on this cut property. And it uses contradiction. So here's the idea. You presume that you have a minimum spanning tree that doesn't include this edge E. So you might ask, okay, so what does that mean? So that means that there exists another minimum spanning tree, and because it is a spanning tree, a question for you. Here's a question. If edge E isn't in the minimum spanning tree, could somebody tell me, how is this still a spanning tree? So what edges does it have to use? So what, like, can you, like, if I were to, like, point my finger at these three edges I have here, so you know this one, this edge E is not in the spanning tree, right? That's what we're presuming. So can this edge be, so I have two edges crossing here. Could this one be an edge in the spanning tree? Yes, it could be. It could be. This one could most certainly be as well. The point is I have other edges that go from, remember, each one of these will have some endpoint that says V1, and then there's going to be another one that's going to be in V2. So most certainly, at least one of these other edges has to be in the spanning tree. So note that these could be edges, these other edges I have here, these could be edges in the MST, in the proof. So I'm presuming that E isn't in it. So now there's a thing I got to think about when it comes to trees. So suppose that I added in edge E. Suppose I took this minimum spanning tree that I'm presupposing doesn't contain E, and I make a new tree that contains E. I have a question for you. Is it still a spanning tree? In fact, an even bigger question, is it still a tree if I add in edge E? And I want you to think back to those properties I was talking about when it came to trees. So remember when I talked about trees, I mentioned some interesting things, equivalent ways we could talk about a tree? There's one of those. There is one specific one that addresses this. So if I add another edge into my spanning tree, is it still a tree? And remember, the graph is already connected. There's no weird stuff going on with that. But if I add another edge in, what happens? So imagine I have a tree. What happens when I add in an edge into that tree? So I'll kind of doodle off to the side here to help you think about this. So suppose I have a tree. So if I add an edge right here, is it still a tree? That's not a tree, right? There's a cycle right here. The exact same thing happens right here when I include edge E. So notice if I put this in, there is going to exist a cycle. Yes, it breaks out the property of the number of, so remember, the number of edges is indeed going to be one less than the number of vertices, indeed. But notice it doesn't have any cycles in it, right? But if I add in one edge, I'm going to guarantee the existence of at least one cycle. So that means that one of these edges is going to be a part of some cycle. And now here's the neat part. It's a spanning tree, right? So that means that there's going to exist some cycle. And here's the fun part. This cycle, there's going to be some edge in here that I can pick. So this is something that's in the proof. But there is going to be one of these edges I can pick. So I'll call it E prime. So I have an edge that's E prime that's going to cross over this, what we refer to, and this is where the name of this proof comes from, or sorry, this theorem comes from, is that these edges form, graph theoretically speaking, what we call a cut, where edges go from one side of the cut to the other side of the cut, and the vertices on this side are on this side of the cut, and V2, all the other vertices are on the other side of the cut. So these are what we call cut edges. And the thing is when I look at E prime, suppose that this is a part of the cycle that includes this edge in it. What I could do is I could swap E prime with E, and I could just simply consider that now. So if I have this edge here, and this edge here, and suppose I swap those two. And suppose that because keep in mind, remember, this edge has to somewhere go from one vertex to another vertex, from V1 to V2, in particular, that one over there. So the question is, if I swap E prime with E, have I reduced the cost of the tree, or is it the exact same cost? Or is it worse? So remember the definition of what E is. So the point is that there's going to be some edge, and it's going to have the exact same endpoints. So like this guy's going to have the same endpoints, or it's going to be some edge that's going to have those same endpoints because E isn't in it, right? So there's going to have to be an edge like E prime that's going to have the same endpoints as these two, as E has. So if I switch E prime out with E, does the cost go up, or does the cost go down, or stay the same? Well, remember, E is a least weight edge, right? So if I switch E prime out with E, the cost either stays the same or it gets reduced. But the point is that this now, when I switch out E prime, so if I no longer consider E prime a part of the minimum spanning tree, the presumed minimum spanning tree, remember, we're assuming that this other one is a minimum spanning tree. If I switch out E prime with E, it's still a spanning tree. But at the same time, it has at least the same cost. It's either improved or it is the exact same. So that means that whatever I just did now is still a minimum spanning tree, right? So if it improves the cost, most certainly my original assumption's false. It was never a minimum spanning tree, but it may actually have the same cost. But the point is I'm preserving the fact that it's a minimum spanning tree. But here's the idea. If whenever I pick one of these least weight edges, I always do that one because it has the smallest weight. If I had a different one that had the same endpoints as this one and this one, let's call it E prime, then most certainly I could swap it and either the cost improves or it stays the same. But if it originally was a minimum spanning tree, most certainly it has to stay one, right? But yeah, you can formulate this using contradiction. If you assume all the edge weights are distinct, you'd get a pure contradiction, meaning that because there always is one minimum spanning tree, then you would always improve it, yielding a contradiction. Or if you frame it more as, I do this tweak to the graph, and I end up with a graph that, a minimum spanning tree that has, I end up with still a minimum spanning tree, that most certainly means that it remains that way, and it's just as true. Either way we formulate it, we still get a minimum spanning tree, and it contains E. But I encourage you to take a look at the proof. It's really nice and elegant. I like the argument. In fact, the correctness of this algorithm can be easily cast in terms of this cut property. So when I get to actual algorithms, you can actually use this cut property to directly invoke the correctness of the algorithm if you take it together with something like mathematical induction or even contradiction, just repeatedly applying it over and over again. But yeah, so this, I'm hoping I gave you some flavor for how this works. The whole idea is that there's some other edge because there exists a cycle, and I could switch out this edge here with a better one. But the point is that this edge here has the same endpoints as E does. But anyways, with that being said, you might ask, what the heck does this cut property do? You might ask that, right? It's a very natural question. So what can we do with this cut property? Because you might look at this and say, okay, all you did is tell me that there's some minimum spanning tree with that edge E in it, right? You might tell me that. You say, Dan, what the heck are we going to do with a cut property? So let's talk about that. So now you might ask, Dan, you'll notice that there's two sets of vertices. There's the ones I have V1 and V2, right? So what does the cut property imply? So this is how we're going to use, there's a couple different ways you can use the cut property. These are at least two different ways. For example, you could literally follow this proof, so the one that's in the notes, and you can actually derive an algorithm that computes minimum spanning trees by just simply always performing these swaps over and over again. It's called cycle deletion. If you ever want to go look it up, it's called cycle deletion. It uses this cut property in the most literal way, but there's other algorithms that do exploit this property very nicely. So what does it imply? So if we have two sets of vertices, if we have two sets of vertices, V1 and V2, if we pick a least weight edge, whose endpoints sit in both V1 and V2 across the cut. So remember, those are the edges that cross from one side of the cut to the other. Across the cut of V1 and V2, it belongs to some minimum spanning tree. That's the big point. So as long as I maintain two sets of vertices, so suppose I have two sets of vertices, and I just always make sure that I always pick an edge of least weight from one of these to the other, where one endpoint's in each of these. As long as I can guarantee I do this always, and I pick a least weight edge, I can guarantee it's in some minimum spanning tree. That's how we're going to use the cut property. And there's a couple different ways at least we can use this. So the first one, I'm just going to mention it. I'm just going to give you a high-level view of it. I have an example of it in the notes, but I'm not going to examine you on it. But I want you to take a peek at it because it's one of the two better known algorithms for solving this problem. I just want you to be aware of it. I'm not going to test you on it, just to be very clear. The first example of how I could use this is called Kruskal's algorithm. I'll focus more on the latter of these two. called Kruskal's algorithm. Here's the idea. You grow a forest of minimum spanning trees from seeds. And I must stress that these seeds are just isolated vertices. So you gotta think of it almost like I'm building a whole forest of trees that eventually become one super tree. So I'm gonna build a whole bunch of these tiny little minimum spanning trees. By definition, by the way, all the vertices, if you think of each subgraph, so if I look at a graph that just contains a whole bunch of isolated vertices, each one, if I only consider that one vertex as a subgraph, if I only look at that subgraph, with respect to the subgraph, it's a minimum spanning tree, because it only contains one vertex, right? So the whole idea is, I imagine I take one subgraph, which only has vertices that belong within its set of vertices, and then I simply have this other set of vertices that are a part of another subgraph. And the whole idea is I would like to find an edge that connects the two subgraphs together to form a larger subgraph. But the idea is that inside of here, I'm going to actually be growing minimum spanning trees. So I'll have one sitting in one of these, then I have another minimum spanning tree in the other one. And the idea is I always pick a least weight edge to form a larger minimum spanning tree amongst those two by merging them. So it's going to be kind of interesting. I like to think that like I'm growing a forest of minimum spanning trees. Like I'm just the gardener and I'm just coming along trying to harvest where exactly these trees should go. So my goal here is I always pick the least weight edge that connects them such that I don't perform or create a cycle in the graph. So here's the idea. So at the beginning, every vertex begins in its own cluster. I'm using cluster in air quotes. It's more of a vague idea for what I just described a moment ago. And I say each cluster is a set of vertices. The set of vertices. In each cluster, the algorithm grows a minimum spanning tree by selecting a least weight edge that joins two of the clusters by joining two of the clusters. For some reason that looked like a weird distorted W there. Joins two of the clusters, growing spanning forests. So we're going to have spanning forests that are eventually going to become, a spanning tree by repeatedly just simply merging them by simply picking a least weight edge every single time such that I don't create a cycle. Meaning the whole idea is I imagine each one's in its own little bubble. So I have a whole bunch of set of vertices, each in their own bubble, and I select an edge that's going to join those two clusters and merge them together. And the whole idea is I always pick a least weight edge. So the way Kruskal does this is you actually just simply sort the edges from smallest to largest by their weights, and you just simply go through this process that I've just described here. So you just simply stop this process when the number of edges added is n-1. And if the number of edges is n-1, you know it's a tree, right? It's not a forest anymore, it's a tree. And that's how you end up with the minimum spanning tree. So the whole idea is in each one of these clusters, you're going to be maintaining minimum spanning trees with respect to each cluster, but it's really a forest of them. And the idea is every time I add in an edge, it brings two of these clusters together. So I put an example in the notes if you're curious about this process. I encourage you to take a look at it. Now, the other one, the other algorithm, so you might ask, Dan, how does this have to do with the cut property? Well, think of it. Each cluster, you can think of cluster 1 as V1 and another cluster as V2, so I have cluster 2. If I pick a least weight edge that connects V1 to V2, this is no different than the cut property I have over here. Does everybody see that? So I could just simply take any two clusters, and those are just sets of vertices, and I just apply the cut property. That's how you get the correctness of this algorithm. It actually just falls right out of the cut property. Just the ideas of just there's this extra step where we have to think about, oh yeah, now I have multiple sets of vertices, so which ones do I pick? And this is dictated actually when you implement this algorithm by sorting the edges from smallest to largest, and you pick off the endpoints and you determine which cluster you're going to pick from doing this. Now, one way you can implement this, a more standard way of doing this, is using a union find data structure, disjoint sets. So I'll just mention that. I'm not going to be talking about those, but they're very fascinating structures I encourage you to look into. So they're called union find. It's union find disjoint sets. So it's a kind of disjoint set data structure. So if we had more time in this class, I would show you that. It's an interesting data structure that has all sorts of different ways you can optimize them further with other sorts of heuristics you can do with them. But I wanted to just mention this because I want to give you a flavor for what's out there. So the one I want to focus on for this lecture is Prim's algorithm. So sometimes people call it Prim-Jarnik. So I'm going to be talking about that one for the remainder of the time. So this Prim's algorithm is like, I don't know, the best way I could describe it is Kruskal's. It's a little bit more complicated in the sense that we grow these clusters, right? And I have two sets of vertices and I just join them together. I form those two clusters, I join them together into a larger cluster. Now suppose you take the cut property that I have and you imagine I start off with one vertex. So suppose I start off with one vertex in V1 and all the other vertices are in V2. And here's the idea. Suppose I always pick a least weight edge from V1 to V2, and every time I introduce one of these edges, I make it hop into V1. So I'm going to take each one of these vertices that I have over in V2, I'm just going to say, hey, look, I'm going to pick a least weight edge from you to me, and I'm just going to put you into V1. I like to think of it like a blob. So let me just give us a high level look, and then we'll start talking about this algorithm. We'll do some examples. So the other one is Prim's algorithm. So some people call Prim Jarnik. This is because Jarnik can claim up to because came up with the algorithm before Prim did. But it's often called just Prim's algorithm or Prim Jarnik. Here's the idea. I think it's very natural if you think of the cut property just as two sets of vertices, and every single time I'm going to introduce another vertex into the first of the two sets of vertices, like a blob that's going to devour the entire graph. So imagine the blob. I'm not sure if anybody's ever heard of a movie called The Blob. There's several incarnations of it, some more spookier than others. And in the movie, the idea is that there's this blob that gets released, whether it comes from space or comes from some other place. Now, I'm not going to get into the details of it because it gets quite morbid, but the idea is that this blob goes around and basically engulfing everything around it. And here's the idea. Imagine it starts in one spot, and then what happens is as it goes around, it's going to start devouring the graph. And you think of the location just like the blob devouring places or all sorts of other things. So I'm going to get into detail about that, but I just want to give you, just in the same vein I talked about Kruskal's, here's the idea. Grow a minimum spanning tree from a seed, so just one, so just a vertex, so you have one vertex that you're going to just start this at. So the idea is to start with V1, having a start vertex. Sorry, that's a start vertex S, and grow a minimum spanning tree by always selecting a least weight edge that crosses the cut of V1 and V2. So the idea is that as I do this, I'm going to start off at vertex S, and every time I'm going to imagine S is in V1, and every time I'm going to do this, I'm going to include another one of the vertices from V2, and I'm going to just imagine like a blob gobbling up that vertex. It's very, very hungry that day. So the idea is that I'm going to have V1 just having a start vertex, V2 is going to have all the other vertices in it, and I'm just going to have it where it's just going to keep picking least weight edges that cross that cut. It always picks a least weight edge, and as this happens, the blob, if you think of S being the initial place where the blob starts, I'm going to have it where the blob's going to have more and more vertices it's going to discover as it does this process. That means I'm going to have to take into account whatever is the least weight edge from the vertices that are in V1 from those that are in V2. So, that being said, I like to think of, so I'm just going to say think of V1 like a cloud. Some people like to use the more softer, gentler way of thinking of it, like a cloud that fogs in, like a cloud. I like to think of a blob because it's just way more edgy. A blob that envelops vertices and grows or expands by selecting least weight edges from in the blob to some vertex not in the blob. So that's a very simple way of thinking about it, is that I'm going to start off with the blob at some start vertex, and what's going to happen is it's going to envelop the entire graph when we're done. So all I'm going to do is the blob is just going to be very, very lazy. So this blob is lazy. It just simply goes towards whatever from the perspective of the blob, which is engulfing the graph, whatever its ends are, it's just going to be like, ah, man, where can I go next? Well, all of me is all over the graph. Which one's the next one easiest for me to engulf? Well, it's the one that is the closest to me. But what's the one that's closest to me? Can somebody tell me what's the closest one? Say, imagine me just in the corner, just like over there, and I'm just like this blob. Don't imagine that in your dreams, okay, everybody? So imagine there's just some blob in the corner over there, and say, I'm the next closest thing to it. So what would that represent in a graph? It's a least weight edge, exactly. So that's all Dijkstra, sorry, I was about to say Dijkstra, but Dijkstra does something quite similar. We're going to talk more about Dijkstra a little bit later, but Prim's algorithm, that's all Prim's algorithm does. So if you think about it, it's always selecting the closest vertex from every vertex that's in the blob. It's very natural to think of it like that. So it's always select the least weight edge from a vertex that's in the blob to a vertex that's outside the blob. So let's talk about this. So I need to give you a couple remarks before we proceed to our example. And here we go. So I'm just going to make some remarks before I proceed. So a couple remarks. So the first thing I should point out is that classically you can implement this algorithm using arrays. I'm going to show you more of an OO way of looking at this that can easily be modified into an array-based approach. So I'm going to start off with what some people would refer to as the array-based implementation of prims. Now, I'm not going to be using arrays, but you can have in this array an array D that stores the least weight edges, edges as we find them. So you may even just store the number. So if you just store what the edge weight is, that's sufficient. It's like what its value is as we find them. And an array P of predecessors. So if you're not sure what predecessors means, I mean parents. So you know how when I formed, for example, the BFS tree the other day, you know how I had a parent attribute where I was able to trace back to wherever I started? So I used that the other day, right? Where I had a parent attribute in my graph when I did BFS, for example. I'm going to be using that same idea here to be storing the predecessor. So what does that mean? It just simply means the vertex that I needed to get to where I currently am. Another way to think about it in terms of the blob is that's the appendage of the blob that got to me, okay? So that's all it is. So I'm going to be maintaining the distances. So these distances in another algorithm I'm going to show you is literally a distance. In Prim, all it is the value of the least weight edge I found so far, the best one I've found so far. So what I'm going to do, just to make this simpler for ourselves, so you can classically just, if you think of the values I'm going to show you in our example, all you do is you'd have two arrays and you just store indices of the least weight edge with its with whatever the least weight edge is, or you'd have it just simply being, in our case, it would just simply be each vertex has whatever the smallest distance is to get to it, which is normally how it's done. And then you just have another array that just tells you the index of the vertex that is the one I get to or go to back through the graph, so wherever the blob started. You'll see what I mean when we see the example. So what I'm going to do instead to keep this simpler, because I want to show you also how you can do this in an OO fashion, because I like to show you different ways of thinking about these things, is I'm going to imagine, just akin to what I talked about when I talked about graph traversal algorithms. This says imagine, by the way. It says imagine we store each of these values with a vertex object. Directly. So I'm going to have two attributes that each one of my vertex objects will have. They'll v. So if I have a vertex v, I'll have v.d. So this is going to be the least weight edge of the current one I found so far. At the beginning of this algorithm, they're all going to start off with some value that's going to be so big that you won't be able to ever beat it in terms of being larger than all the other edge weights. You just think of it as infinity. So I'll have this. And then I'm also going to have v.parent, which is going to store the predecessor or parent. So each vertex is going to have these two attributes. So you're going to see it in our example. I assure you, it sounds like I'm laying a lot of stuff on you, but it's really nothing. So just remember, I'm just doing this where I'm storing each vertex, all this information with the vertex objects. The only difference would be with this purely array-based approach is you just have each index representing a vertex, and you would just have whatever D is in D, and you'd have whatever parent is in P for each vertex, because the vertices are labeled from 0 up to n-1. So anyways, let's proceed. One other remark I want to make before we get too ahead of ourselves is that wherever I start, the parent will be initially set to be null, but all the vertices I'm going to presume get set up appropriately. So when you actually see the algorithm, you'll see this play out. So let's kind of just walk through the idea first. So question. Would you rather see the pseudocode first, or do you want to see the example first? We could go either way. So I must stress that I will be showing you a faster implementation of the algorithm next class. But I thought I could do either way. I'm flipping a coin. So let's just do, let me just write out the pseudocode and let's proceed first that way. And then we'll do an example. So I'm just gonna top load the algorithm because we already know the main idea. I'm gonna have this blob that's going to form and envelop the graph. So I'm gonna have some start vertex in my variant of Prim here. So I'm gonna give the algorithm here. It's gonna be Prim. I'm gonna give you a connected undirected graph. So I'm gonna give you a connected undirected graph is equal to G is equal to VE. And I'm gonna have vertex S, which is one of the vertices in the graph. So that's just our start, or some people would refer to that as the source. Makes more sense in the next problem I'll talk about next class. So the output will be a minimum spanning tree of G. Now I must stress that this algorithm doesn't return anything, but you can easily modify it to do so. Just to be very clear. I'm just going to store the tree in Prim by modifying the parent and what those D values are going to be for each vertex. But I'll mention where the vertices and the edges get selected at every point. So if you ever find yourself intrigued to explore how you could add each edge of the minimum spanning tree into a set of vertices or set of edges, you can easily modify what I have here. So anyways, as I said, there's some setup initially. So I'm just going to have for each vertex V of G. So you're just going to go through all the vertices in the graph. You're going to do the following. So start off by assigning each one of the D values for each vertex to be infinity at the beginning. And I'm going to set their parent to be null. So none of them are going to have a parent or predecessor yet because the blob has not done its fun stuff yet. So I'm going to start off by planting the blob at vertex S. So I'm just going to imagine the blob just plops down at the vertex S. So it means that the blob, as far as it's concerned, it doesn't have anything else to do. It just starts at S. So I'm going to set its D value to 0 because it's already going to be included in my tree. So I'm going to start off by doing it so that I always pick the start vertex at the beginning of this process. So what I'm going to do is I'm going to have a for loop. For I is 1 to n, I'm going to do the following. So I must stress that this is performed n times. This is done once per vertex. So I'm going to start off by assigning two, what some people call sentinel values, but I'm just going to have them so they're initially set so that I can break them in some tie. So I'm going to have a variable I'm going to call dmin. This is going to be keeping track of the smallest D value. So remember, these D values are going to keep track of the least weight edge that I've encountered at that vertex. So if I could find a closer way for my blob to kind of slop over to devour it, I want to make sure I update these later on, which I'm going to do afterwards. But I want to make sure I always pick the one that's the laziest approach for the blob to do so. It's whatever's the closest to that vertex. But remember, each vertex I'm talking about is in the blob, so you have to keep that in mind. So I'm going to have this other variable called umin. It's going to keep track of the additional information associated with whatever vertex I pick that breaks or is the one with the smallest D value. So what we're going to do is we're going to find an unmarked, so we're going to find an unmarked vertex with smallest D. So I want to find the one with the smallest D value. And these D values are going to get updated each time I do this main for loop here. So I'm just going to presume I have all of these going through all of my vertices, and I'm just going to pick the one with the smallest value. But you'll notice at the beginning of this process, all of them start off as infinity. So if I set the start one to be 0 for its D value, you know you're going to pick S first, right? So the blob is just going to say, I'm going to consume S. So that's what's going to happen in the first iteration of this. So for each vertex U of G, we're going to do the following. So for each one of the vertices, I just check if U is not marked. So we're going to be marking vertices in this algorithm. And U dot D is less than D min, meaning I found a closer vertex to the blob. Then we update U min and D min. U min is going to be assigned to be U because I found a better one. And D min is going to be assigned U dot D. So I'm going to do this. That ends the innermost for loop. Now I'm going to have to give you another for loop, but I'm going to, before that, I'm going to make sure I mark umin. So I'm going to mark umin. So when this happens, umin joins the blob. So this is right when the blob decides, I've devoured that vertex. It's me now. It's just me. It's me, the blob. So anyways, let me write out the part that updates the edge weights. Actually, let me keep this over here. I can write the rest right here. So I'm just going to come right up back over here. This will work out just fine. So let's do this. So I'm just going to go through for each incident edge. So for each umin v, so I'm going to look through all the incident edges of umin. So for each one of these, we're going to do the following. So I'm going to see if I have a better least weight edge. So if I discover, say the blob finds a better one, we want to take that one if possible, but I need to know they exist. So I'm going to update my D values because the blob will be uncovering more of the graph as we do this. So if the weight of umin v is less than v dot d, then, so if it's the case that the weight I've currently found is better than what is currently sitting at v, so what I'm going to do is update v dot d because I found a shorter edge. V dot d is going to be the weight of umin v. I'm going to update the parent of v. and this would be at the end of the main for loop. So that's Prim's algorithm. So you might ask, Dan, what is this all about? So just a quick thing, I would just want to recap kind of the main pieces here. First, the initial setup. This sets up the initial D values so that they're large enough that I always can beat them. Because remember, I haven't yet explored all of the graph. The blob starts at a beginning point in the graph and it will envelop the entire graph, but it has to uncover that graph as it does this process. And I haven't yet formed the tree at all. So I start off at S, and then I go through each one of the vertices. I go through each one, this whole process. I do it n times exactly. And for every single one of these, let's see, is it still within, yeah, this is all within that outermost for loop. So this is the outermost for loop this is closing on, just to clarify. So this is when I'm actually like, this is straight up like there's this for loop here. It goes from I is 1 all the way to end. It ends over on that board. So I go through each one. I pick the one with the smallest D. The blob devours that vertex by marking it, and then it simply updates all of the distances or least weight edges. That's why I call it D, because you think of it like a distance. But it's not it's a distance from the laziness of the blob. There'll be a more intuitive way of thinking about the D values for another algorithm I'll show you that's very similar to this one. But we have about a minute here. I have a question. Would you rather I stop here now, and when we come back we do an example using prims, but I ask you to look at the time complexity analysis? Or would you rather that you take a look at the example in the notes, which goes step by step through executing this algorithm, then we do the time complexity analysis when we get back? I'm good with either one. So far I got one for analysis in class. Yeah, because you'll find that the example's very intuitive. But, so what I'll do is I'll quickly, I think I'll meet everybody in the middle. How about this? We'll do both. We'll do both. But what I'll do is when we come back, I'm going to go a little faster through the example. So I'm going to post the example in the notes. So take a look at it, and I'm going to go a little faster through it for the sake of completeness. Because I think it's important that you see one example in class with me. But just to confirm that you're understanding it. So anyways, we'll come back and we'll do that next class. And we'll finish up talking about Prim's algorithm next class. And we'll start talking about Dijkstra's algorithm for single source shortest path problem next class as well. So anyways, I'll see everybody later. So have yourself a beautiful day.